Hi there, my name is Bojan, and it's my pleasure to present, together with my fellow co-author Peng, our work entitled Nearest Neighbor Classifiers over Incomplete Information. At its core is a study of how we can take the notion of incomplete information, view it through the lens of database theory, extend it to the context of machine learning, and apply it to make the process of data cleaning less painful. The result is a method which we call CPClean, designed to make data cleaning more cost-efficient. This project was a joint effort between many of our collaborators from ETH Zurich, Georgia Tech, and Microsoft. Our focus is on the common machine learning workflow. It's made up of a training dataset, a model, and a validation dataset used to make predictions. The assumption under which we operate here is that the training data is clean. This means that all values that appear in it represent known facts. However, due to data acquisition process that is usually pretty complex and noisy, we often encounter values that are either missing or wrong. A common term for this is dirty data. Another one is incomplete information. Data cleaning is an entire discipline devoted to repairing this dirty data by some approach of identifying and correcting the mistakes. This process can be automated or manual, but in any case, it is often expensive. So a natural question is, can we make this cheaper by cleaning only a subset of data? If yes, which data example should we prioritize? And on top of that, can we skip cleaning altogether? To answer that question, we make a few key observations. First, each dirty value induces a natural uncertainty, as we may have a multitude of possible ways to repair it. Second, all the uncertainty in the training data is transferred to the uncertainty of model predictions. Third, each data repair induces a reduction of uncertainty on both sides. In this context, we care about model predictions. As a result, the strategy we propose is to prioritize cleaning the examples that have the biggest impact on reducing the uncertainty of predictions. On top of that, to answer the question of whether we need to clean or not, we again look at the notion of uncertainty. If the model can make a certain prediction, the uncertainty of predictions is gone. Then any uncertainty in the training data doesn't really matter, and there is essentially no need to clean the data. Now, the next question is there a way to compute this impact? And even before that, is there a principled way to reason about uncertainty in this context? These are the questions that sparked our interest, and in the following minutes, we will go over some of the main things we learned. In our work, we try to answer three key questions. We look for a principled and logically coherent framework that would enable us to reason about uncertainty in the data. To make this framework practical, we also look for algorithms for answering queries about this framework. Finally, we show how it can be helpful at solving the original problem of reducing the cost of the data cleaning process. As database people, when faced with a problem like this, it is natural to ask, how do databases deal with issues of uncertainty? Starting from a table which contains an uncertain or dirty value, we examine how one would go about answering a simple SQL query over this data. But first, we should ask, how does a database even represent unknown values? This is the purpose of the special null value, which is used to signify that we don't know the true value of some attribute. Now, formally speaking, what would be the semantics of this null value? In plain language, the meaning of null would translate to I don't know. But the question is, what does that really mean? Well, it's actually a tricky question that leads us deep into the rabbit hole of database theory. Needless to say that it's quite involved, but to give you a gist of it, let's go over two key insights. The first one is that if we don't know the correct value, we need to consider all possible values. In the case of our table, we need to expand it into a whole set of tables where each one is defined by a distinct value we could assign instead of the null. We call this the set of possible worlds. Now, to answer the question over the unknown value, we need to consider what would be the result of that query in every possible world. As we can see, the result may not be the same in all possible worlds. This is where the second insight will be of help. Namely, when reasoning about uncertainty, we should nevertheless do our best to answer queries with certainty. In the case of our particular query, this means that the result should contain only the tuples for which we are certain to belong to the result. And here, those are the tuples that appear in every single possible world. In other words, for each possible result tuple, we should be able to make a decision if it certainly belongs to the result or not. The next question is, could this notion be translated to the world of machine learning? In other words, can we reason about the uncertainty of model predictions even though we are starting from uncertain data? Let's look at our table again. And this time, look at what should happen when we use it to train a machine learning model and make a prediction on some validation tuple. Following our previous logic, we should expand the table into all possible worlds, And we should look at what would be the query result in each possible world. In this context, the query result is actually the model prediction. So if all models predict yes, then we can say with certainty that the answer should be yes. The same goes for no. If all models say no, then the answer is certainly no. Now, in the likely case, when some models say yes and some models say no, what will be the only certain answer? It will be, I don't know. There's an interesting thing to point out here in the context of data cleaning. Namely, if a model is able to give a certain yes-no answer even though the data contains dirty values, is there any need to clean those values? Well, given that however we clean, we always arrive at the same result, the answer is certainly no. The question of whether a model can make a certain prediction or not is what we refer to as a decision query, and we use it later on to help us detect if a dataset even needs cleaning. Another useful type of query is what we call the counting query. Namely, assuming that we cannot give a certain yes-no answer, we still might want to know how many possible worlds would give a yes answer and how many possible worlds would give a no answer. This query will become the essential piece of our cleaning algorithm, which we will talk about in a few minutes. But before that, we need to see if the mentioned decision query and counting query can be answered in a practically feasible amount of time. As you probably noticed, when dealing with unknown values, our logical framework requires us to reason about all possible ways to repair that unknown value. Furthermore, as the number of unknown values grows, the number of possible worlds grows exponentially. Specifically, if there are n tuples with unknown values, and there are n possible ways to repair each tuple, then the number of possible worlds is on the order of m to the power of n. On top of that, in the machine learning setting, to answer our question in a semantically correct way, we need to train an ML model in each possible world and then obtain its prediction. Clearly, if we are dealing with a general classifier that we view as a black box, the situation looks very discouraging. Both of our queries become intractable for any practical dataset. We could of course give approximate results by using Monte Carlo methods. Still, we were curious if it is possible to find some assumptions that would allow us to give exact answers, even though we are trying to reason about a space that is exponentially large. This pursuit led us to explore a widely known model that has a very simple structure, the k-nearest neighbor model. With this model, we are able to construct algorithms with the complexity that is polynomial in the size of data. Furthermore, for the special case of the one nearest neighbor model, the decision query can be computed in time that is linear in the size of data. Needless to say that these results were quite surprising to us. The algorithms themselves are somewhat more involved to talk about now, but we encourage you to check out our paper if you're interested to learn more. Now, given that we have this logical framework with queries we know we can compute in a reasonable amount of time, the next question is, how can we make use of it?
Hey there, Peng here popping in. I'd like to talk about our methods for applying the certain prediction framework for the task of data cleaning. I'd also like to go over some results that show how well our method works on real data sets. Starting with the main question, how can we drive down the cost of data cleaning? If you recall, our main approach is to prioritize the cleaning effort towards cleaning the data that will have the biggest impact on the uncertainty of model predictions. Measuring this uncertainty was the main motivation for us to develop the previously mentioned logical framework. Coming back to our machine learning workflow with the training data, model, validation data, and predictions. We consider the case where we have multiple dirty values in our data. The question becomes, which dirty value should we clean first? According to our original idea, we should clean the one that has the biggest impact on uncertainty. Furthermore, if there is no uncertainty, namely the example can be certainly predicted, then we can skip cleaning altogether. The question now becomes, how do we even measure uncertainty? Well, if we try to apply some lessons from information theory, we notice that a very fundamental way to think of uncertainty is in terms of entropy. This is where our framework can help us. Namely, if we compute the counting query over our dirty data, assuming a uniform probability distribution over possible words, we could express the resulting possible word counts as entropy. Another insight from information theory is that reduction of entropy and gain of information are essentially two sides of the same coin. Maybe we can use this notion as a measure of impact. To compute the expected information gain resulting from cleaning a specific tuple, we need to compute what would happen to the counting query if we were to clean that tuple. This would again allow us to compute the resulting entropy. The difference between these two entropies is precisely the information gain. Now by repeating this process, we are able to compute the information gain for every single tuple, and then simply clean the tuple with the highest one. Data cleaning then becomes an iterative process of gradual reduction of entropy of model predictions, where the optimal path is guided by maximizing information gain. The cleaning can stop when there is no uncertainty of predictions, which means all the validation examples can be certainly predicted. Well, this might be true in theory, but does it apply in practice? Let's find out. We evaluate our approach on 5 datasets with synthetic missing values and 1 dataset with real missing values. For synthetic missing values, we simulate 2 types of missingness, including random missingness and systematic missingness. We compare our approach with several baselines. The first baseline ground truth uses the ground truth version of dodgy data to train models. The second baseline default clean uses mean or the most frequent value to impute missing values, which is the most commonly used cleaning method in practice. We can see that there is a gap between the accuracy of the ground truth and the default clean. For the remaining baselines and our CPClean, we report how much of this accuracy gap can be closed. As you can see, CPClean generally closes more gap than all other baselines, especially under systematic missingness. In most cases, CPClean is able to close almost 100% of the gap, which means its accuracy is as good as the ground truth version. The average percentage of examples needed to be clean is about 50%. Actually, on some datasets, CPClean is able to close all the gap by cleaning only 20% of data, which means using CPClean, cleaning about 20% of data is as good as cleaning the entire dataset. In practice, users may have limited cleaning budget, so that users may choose to terminate CPClean early before all the validation examples become certainly predicted. For example, on the bank dataset with systematic missing values, CPClean needs to clean about 80% of data to be finished. However, users choose to terminate CPClean when 50% of data are cleaned, because they don't have more cleaning budget. To study the performance of CPClean in this case, we compare it with random clean that randomly picks examples to clean. As you can see in the figures, with the same number of examples cleaned, CPClean can close more accuracy gap and make more validation examples certainly predicted than random clean. For example, by cleaning 50% of data, CPClean can close about 20% more accuracy gap and make 30% more validation examples certainly predicted than random clean. This means even if we terminate the CPClean early, it is still significantly better than just cleaning data randomly. To recap, let's go over the main contributions of our work. First, we develop a logical framework that allows us to deal with uncertainty in the context of machine learning workflows. We define the checking query and the counting query, which enable us to reason about model predictions over the whole set of possible words. Second, we show that for the k-nearest neighbor classifier, we are able to give exact answers to those queries, even though they have to be consistent with exponentially many possible words. And third, we show that this is indeed a useful framework with a practical impact on reducing the cost of data cleaning. We do this by showing how our counting query can be used to compute the information gain resulting from cleaning individual tuples. We use this as a measure of data importance and show how it can help us to determine which tuples we need to clean first. We also argue how the checking query is semantically equivalent to checking if cleaning is necessary at all. Finally, we combine all of the above into a method called CPClean that is able to significantly reduce the cleaning cost while preserving the model performance. Thank you very much for your attention. On behalf of my fellow co-author Bojan and myself, I would like to thank all our awesome collaborators, our colleagues Renzhi and Merve, our Microsoft collaborator Wentao, and our PhD advisors Xu and Ce. This work would not be possible without their devoted effort. Finally, feel free to reach out to us in case you find this topic interesting and would like to discuss. Thank you.